Welcome back to the shop. It's good to see you again. In this episode I finish off the crash-proof bed, that's not easy to say, on my CNC router. This worked out really well. It's got to the point where it just doesn't want to break a tool. If you crash it, it stops before it actually breaks the tool. Brilliant, utterly brilliant. I'm really pleased. If you want to just see the testing at the end and not bother with how I actually got there, I'll put on the screen down below here where you need to spool to in the video. But for those of you who want to watch, we'll roll the titles and we'll see you on the other side and I'll explain what we're up to. So if you're a regular or even regular viewer, you'll have seen this CNC router before on more than several occasions. When I did the rebuild on it, I put an isolated aluminium layer. In there is the aluminium foil layer, and these are the hold down screws, bolts, with M6 threaded inserts all over the bed. What I'm trying to do here is make it so that if the tool touches any part of the metal bed, a hold down screw or ploughs into or the tool accidentally ploughs into the bed and then hits that aluminium foil layer, it triggers an e-stop. And to do that, what I'm doing is putting a small voltage, 5 volts, on the bed, and then detecting if the tool touches any metal part, it shorts it to ground, and then I can pick that up with an Arduino and trigger via a relay the machine into an e-stop. This is a single board computer called an Arduino, readily available, cheap as anything. I think they're about £5 a piece, if that. And this is a little relay module that simply plugs into it. The programming is relatively easy as well, so yeah, cracking little devices these. So in theory, if it crashes, it should stop. In theory. In practice, there is so much noise that the Arduino is triggering spuriously, and I've tried to work out a way of getting around that. And I may have a possible solution, but the other issue that I had, which you've seen in a video a couple of episodes ago, was, and I didn't know this, I had no idea, never seen this on YouTube anywhere before, but as soon as a bearing is a short circuit while it's stationary, the moment it starts to move, it becomes isolated. I think as the grease gets distributed around the ball race, then the balls actually no longer make connection with the cage, so consequently it becomes an isolated system, and that is a real pain, because as soon as the tool moves, it becomes disconnected from the circuit and it can't detect a hit, a touch, or a crash. So that's why I fitted a tiny little carbon brush out of an old carbon motor. There's the little carbon brush that connects the spindle directly to the case of the machine, so it keeps connection even when it's spinning. So anyway, that's by the by. I think I have a possible solution with this bit of kit. So what is this bit and what does it do, I could hear you say? Well, it's an optoisolator, and what it does is it provides complete galvanic isolation. That's a hell of a sentence. For the two halves of the circuit. So what's effectively in here is, on one side you have an LED, and you could send a signal, 5 volts, whatever, into your LED. That will then turn it on, and turning that on, it's inside a little tiny piece of black plastic so that you can't see it, and in fact it may even be infrared. And connected to that but isolated from it, so in other words they're physically separated inside this chip, is a photosensitive transistor. And that transistor, or a photosensitive diode, they operate in a similar way in these for this, that will go short circuit when it picks up light from the LED. But there's no physical connection between the two. So that makes it possibly an ideal solution for the noise that this machine picks up. This big isolated layer, this aluminium foil layer that occupies the whole bed of the machine, is a bloody good aerial, and it's picking up all of that noise. My power supply is set to 5 volts, and to save me using a current limiting resistor on the LED, I've set it to its minimum current, which is 25 milliamps. So that's on. On the breadboard, you have to ignore all the other bits and pieces on there. I'm too lazy to put them away. I've got a little tiny LED, 3mm LED, which is connected to the machine. I've connected the ground of my power supply to this cooling fin to ground that side of the power supply. And if I pan down, the positive side, 5 volts, comes here and goes into the bed via this screw. So that's connected to this layer. I've also got a probe connected to that as well. So when I touch these two, my LED comes on. What I'll do is we'll just test to make sure that that still works with the machine running, and the LED only comes on when it needs to come on. As you can see, that LED is glowing very slightly. That's the physical embodiment, if you like, of the noise that's in this circuit. So if I just simulate a crash, that comes up nicely. If I turn the spindle on, there we go, that's the minimum speed for the spindle. That LED is not glowing any brighter. And let's see if I can simulate a crash. There we go. That looks very promising. I think this optocoupler isolator seems to have done the job. Let me show you. So if I turn the spindle on, no spurious triggering. I'll run this for a good half an hour just to make sure that it doesn't trigger, but I feel reasonably confident. In fact, I feel very confident. So let's simulate a crash again with the probe. So here we go. There's a crash. It's gone into e-stop, holds that for 10 seconds, then resets. There we are. It seems to work. It seems to work, touch wood. So I think the next thing to do is I'll print up some little trays to hold all those circuit boards, so I can then mount them in the control cabinet here with a separate little power supply, and we'll wire it all up, install it in there, wire it up, and reassemble this motor, and then make something and see whether or not we get a spurious trigger or not. That would be the thing to do. So let me go and do some printing. So here we have 12 volt power supply bolted to the chassis, and this new plate with an Arduino Uno, a relay and an optoisolator also connected to the chassis. I haven't connected the e-stop signal to the actual control system. I wanted to try it out first, make sure I'm happy with it before I do that. Ow! Ow! Oh, there's power there. Ow! So where the hell is that coming from? Something's not right here. Let me take some measurements. This thing is lethal, and I'll show you why. The mains comes in at the back. Hopefully you can see that, and it goes in that orientation. And if you can, hopefully you can see, this pin on the at the back is live, the pin at the front is neutral, and the one in the middle is earth. So coming inside, live, earth, neutral. They've got live and neutral the wrong way round from the factory. I've not done anything with this. I can't believe that. That means that when you get up and you measure the voltage on the main switch, neutral is 235 volts compared to ground, which is down here. Thankfully, and the reason I haven't found this as a fault is because the ground is connected to the chassis, but it's not connected to the neutral. Had it have been, then it would have just taken a trip out every time you plug it in. But I can't believe they've done that. Live and neutral the wrong way around. Unbelievable. Totally unbelievable. What's even worse is I've had this machine for probably 8 years and I've never noticed. I'm staggered. Totally staggered. If you've got one of these machines, it's oh blimey, it's from a company called Nicecut, although I believe that realistically it was made by another company and they just badged with a sticker. If you've got one, looks like this on the inside, for God's sake check it out before it kills you. Unbelievable. Even this ground is something I added when I discovered that just after I bought the machine, if you touch the chassis here and the bed of the machine, there was about 70 volts difference. You could just feel it tingling. You thought, something's not right, so I put an earth between the two. I'm staggered, utterly staggered. Before I go any further, I'm going to put the lid back on this spindle motor, and it seals with two little O-rings that go there and there, so the water that comes in goes through this this top flange and then into the body of the motor, and then swirls around the outside of the windings to keep it cool. So these little O-rings I don't think I'm going to use again because they look green crackered. So I'll put a couple of new ones in. Right, so let's take two of these and go. Let's have a quick recap. I've fixed the wiring issue. The mains is now connected where it should be, and I've added Arduino, relay block, optoisolator, power supply in the back there. The relay output goes to pin 7, X7 on this Rich Auto A11 control system. and that's naturally high, so it's got a weak pull-up resistor in there that keeps it at 24 volts in this case, and as soon as the relay fires it connects it to ground, so it takes that pin to ground. That puts this into E-stop, stops everything. So in theory this should now all work. So the thing to do is to fire the old girl up and see if it works. So far so good, no smoke. So there's the control system as it's booted up, and as you can say, it's do we want to home the machine, and in this case we do not want to home the machine, so move down to there, press OK. Now if I turn the spindle on, press this, that button there turns the spindle on and off, the spindle's now going round. That screw is connected to the bed, which then goes and connects to the foil layer. So that is sitting at 5 volts. The body of the machine is sitting at 0 volts. So if I connect these two together, it should, in theory, stop. How good is that? How good is that? So this machine, there you go. It's, hopefully you can see that. That says user press emergency key. It's now in emergency stop. So if I press OK, now it's back to normal. Now I can turn the spindle on again, carry on machining. So in theory, if this crashes, it should stop. Excellent. Right. That spindle is now doing 24,000 RPM. So this is a good test to see whether or not the brush in the top here is still making contact. There we go. Perfect. Spot on. Right, so here we go with the true acid test. I've got a block of aluminium bolted to the bed. That's firm, that's not going anywhere. In the spindle I've got an engraving bit that I don't, or an engraving cutter that I'm not too fussed about if I crash, if I break. So what we're going to do is turn the spindle on, then drive it into the edge of this aluminium block and see whether or not it actually stops. Not tried it. This is the acid test, as it were. Okay, the spindle's on, and if we go X minus, well, there you go. Well, I have to say that was a bit of an anticlimax. It just stopped. Gone into E-stop. Press OK. It should just stop, reset itself. Alright, it's decided to home. Okie dokie, let's do that again with an extreme close-up. Right, here we go. Wow, that'll live to cut another day. Look at that. Wow, that's in good nick. Excellent. Right, I just popped down the workshop again, and I'd forgotten I'd left this on. I was doing a bit of editing for this video, and this thing has been running now for 3 hours, and it's not spuriously triggered, and we'd know if it had because it would say it's gone into E-stop here, and the only way you can get out of the E-stop is pressing the OK button. So it's not spuriously triggered. I reckon that's quite positive. In fact, let me just let me use this bit of bar and see if I can actually put it into an E-stop now. There we go. Immediately it's gone into an E-stop. Ah, perfect. Perfect. Wow, what can I say? If you made it this far in the video, thank you very much for watching. Please hit the like and subscribe button and spread the video. Hopefully somebody will gain something from this. I think that this is a bloody good idea, and I think that some of the manufacturers ought to start incorporating this sort of thing in their machines, because it's, you know, if you're doing this at manufacture, it's not that difficult to do. It's not going to add much to the cost of the machine, but it can save a load of cutters. Some of these cutters, as we all know, are expensive, and if you occasionally plough one into a steel holding down clamp and you ruin it, that can get quite an expensive hobby. So I think it would be very good if the manufacturers decided to actually follow this, adopt it. Down in the description I have put the code. It's really simple code. I think there's only about 8 or 9 lines in it. It's as simple as I could make it, because and there's a reason for that, because the Arduino is cycling through this code. It's only looking at the pin that detects the crash occasionally. So the faster you can go around a loop, the more often it's looking at that pin. So that's why the code is really, really basic. Anyway, I'm stoked. I'm truly amazed. It's been a long journey to get this far, as you've seen. The machine was badly assembled from day one. I'll put a link in the top to the playlist of all the videos that I've done rebuilding this machine. The wiring was lethal, and I mean that quite literally, bloody lethal. I had no idea, and I've learned something quite dramatic with this, that bearings are connected to they're a short circuit when they're stationary, but as soon as they start to move, they no longer make connection. I think as the grease gets distributed around the balls. So I had to add a little carbon brush on the very top of the spindle, as you've seen in the last video, to keep that connection going while the thing is running. So now the tool is permanently connected to the ground of the machine. That's good. The bed, I think the bed is brilliant. I do think that it would have been better to have put more of these hold down threaded M6 inserts in. I think that would have been a bit more sensible to put like 50% more, because it then makes your hole pattern a lot smaller, makes it easier to hold stuff down. Apart from that, I'm choked. I'm so amazed. It not only works, it works really well, and it's going to save me hundreds of pounds in cutters over the next few years. So fantastic. Make your own. Really not that difficult. Now the groundwork has been done, you know what to do, you know what to follow. Make your own. It'll save you a fortune. Anyway, take care, look after yourselves, lecture over, bye.